All right. Good morning, everyone. Hopefully, you can all see the welcome to the eighth annual OpenVSP workshop. My name is Brandon Litherland. I'm from NASA Langley Research Center in the Aeronautics Systems Analysis Branch. My co-hosts this year are Rob McDonald from Uber and Justin Gravitt from ES Aero. We welcome you to the third day here. We're fully virtual this year, so no fees, no registration, free and open distribution to the public. So feel free to share the links to the workshop page or sessions on social media within your working groups to your friends or anyone you think that would benefit from these talks. Reminder to our viewers, please make sure to set your player quality to 1080p using the little gear icon in the bottom right of your player. Choose 1080p for the best viewing. YouTube usually doesn't do this automatically. Even though it may say auto, it could have something like 480p depending on how it's going. You will need to check this quality each time you reopen the links, so be aware of that. And if you plan on following along with VSP during some of the tutorials, please remember to try and do that on a separate screen. So if you happen to have two desktop screens where you can view on one and work on the other, we recommend you do that. You can also watch these videos through a smart device. And if you have to step away, to deal with children, or if you have to go to class, or if you have a conflicting meeting, these sessions are recorded and you can view these later, so don't feel like you're going to miss out. To our presenters, please remember to close the VSP Live YouTube stream while you present. That can lead to some audio feedback issues, or at the very least, mute that stream. Maximize your presentations to get the best resolution for our viewers. Share or display closest to a 16:9 aspect ratio if you can, and if you're using multiple screens. And only the moderators or the presenters should be on the Teams meetings at any time. So to interact with our speakers, we've got NASA Conferences IO service up and running, and the links to the social Q&A are on the main page and below each player here in this blue link. You simply click +ask to post a comment or a question, and our moderators will either address these directly or forward popular topics to the speakers. Note that you can also chat with us in the VSP Live chat to the right of your video player. We will respond to either one of these. The Conferences IO is the only one that is anonymous, however. We have the workshop session schedule and links on the main workshop page here at the Workshop 2020 Wiki. And we have links on those pages, but to make things nice and easy for everyone, we have all of the links to the sessions here underneath the video description. So if you click Show More right about here, all this will drop down. When we're ready for our 2 o'clock transition to the afternoon session, you can go ahead and click this link right here, and that'll take you straight to session 3.2. So, a word on our technical schedule for today. In the first session, we're starting off with folks from FlightStream talking about flight control analysis and gust modeling for UAM vehicles, followed by some research through ES Aero and UIUC for autonomous differential throttle-based flight control. After that, we're going to be doing some build sessions with Justin Gravitt from ES Aero. First, we're going to be talking about how to build OpenVSP and work with the OpenVSP API. So really interesting stuff all through the morning. And in the afternoon session, we have a focus on structures. So we're going to do some of the VSP structures with Justin Gravitt again. And in the rest of the afternoon, we'll be doing a presentation for Infor Structures Studio with M4 Engineering. So lots of interesting technical work today. And I hope you all are enjoying the workshop so far. We're having a really good time. And with that, I'm going to go ahead and bring our presenters online. Roy, are you ready to go? All right, take it away.
Okay, great. Well, what we want to talk about today is a final report really for an STTR that we just completed. It's a phase 1 where we looked at air vehicle gust response for early design. And so we've been involved with VSP for quite a while, and we've used VSP integrally for this project, and we thought there'd be a lot of interest here. So basically, we're a partner with Auburn University in this case. Dr. Aman Chakraborty is the Auburn University contact on this one, and Aman is going to come on board and give part of the presentation, a good part of it. He's the one that did the flight dynamics and a lot of other things that you'll see here. We did the flight stream and the research and flight part of the project. Research and flight was the or the SBC in this case. So, um, so plate stream basically is a very efficient subsonic inviscid surface vorticity solver. Uh, it started back in about 2013 as a project that we decided we wanted to bring to the commercial environment, and so we've started with some SBIRs from NASA Langley in about 2014, and so we've had several SBR phase ones and STTR phase ones and a phase two and a phase 2E to continue developing flight stream, and it's now become used really around the world. It doesn't need a volume mesh, of course. It's a surface solver. And then it generates results very quickly and robustly for the most part. Physics-based flow separation has been added as part of our phase 1, phase 2, phase 2E program that we've just now finishing up. We offer propeller modeling both in the steady case with the actuator disk theory from Conway, and the unsteady solver allows us to do rotating blades. So we believe our UI to be pretty intuitive, but it's also scriptable. So we've had people running flight stream through these MDAO type environments, and we offer some graphical interactivity in post processing. So we'll move on to just mentioning a little bit about our involvement with VSP. In 2014, we went to the VSP workshop in San Luis Obispo and introduced flight stream to this community, really, with some VSP models. And ever since then, and continuing to today, we use VSP pretty heavily as one of our mechanisms for getting geometry into flight stream. And for this project, we use VSP pretty heavily, and Amon's going to show you some very interesting stuff, I think, that we were able to do with the VSP models. There's several different ways you can get VSP geometries into flight stream. VSP now offers CAD export, which we can exploit and have done quite a few examples with. But then, the thing that we probably rely on the most is CompGeom to do direct mesh creation or manipulation in VSP, and then export that to flight stream. We do now have some mechanisms to do control surface deflection. We're still in the process of refining and improving that capability, but that's a really nice way to get deflected surfaces into flight stream. We're looking at now more robust ways to connect VSP with without having to go through the CAD functionality. All right, so of course we've done a lot of validation studies with flight stream over the years, but for the project that we were talking about here, this STTR has been really UAM related, and so the LA8 configuration at Langley has been a very instrumental piece of our validation for this particular project. And Steve Guether there at Langley has both run the wind tunnel test and done some validation work himself. We followed up on that with some more validation work, and here you're seeing the wind tunnel results from the 12-foot tunnel at Langley compared with the flight stream results. And so you can see why you really need something more detailed than something like a vortex lattice code. We do capture the complex geometric effects here on the aeroloads, and you can also notice that we capture the flow separation pretty well. So really quite pleased with these LA8 validation results. This is just a little bit more to show some of our comparisons. We have a paper at SciTech next year to outline all this in much more detail, but here we're just looking at drag coefficient and moment coefficient. We've been quite pleased with the results on both. All right, so kind of just a little bit of a summary of the flight stream stuff. It's a vorticity-based solver developed by Research in Flight over a period of about 6 or 7 years here to mature. It's now matured into something that we think is very quite capable. For this STTR project, we started developing that additional capability using a tool called CLASP, Control Load Alleviation Simulation Platform. That's Amon's part of this project, and Amon's going to spend quite a bit of time describing that in just a few minutes. All right, I'm going to let Amon talk about the next couple of slides, and I'll come back and talk a little bit more about flight stream.
All right, thanks, Roy. Like Roy mentioned, CLASP is a MATLAB Simulink-based tool that we've created as part of this project in order to study flight dynamics of UAM-type vehicles, especially gust encounters. So it stands for Controls and Load Alleviation Simulation Platform. It's meant to be modular and quickly reconfigurable to be adaptable for different types of UAM aircraft geometry. The idea is to provide a test bed where we can study flight dynamics of novel configurations. We can implement some flight control laws and see how those perform, where we can run the airplane into turbulence and gust encounters, and also where we can study what the structural loads are and the effects of structural flexibility. So our focus thus far has been on basically hooking together this framework and getting it to a point where even if the underlying analyses are somewhat simplified, we have a proof of concept of the integrated functionality. So CLASP allows us to model sensors and flight control laws, as well as gust load alleviation algorithms and the dynamics of control effectors. So for instance, a control surface is an example of a control effector. Propulsors for UAM type of vehicles are also examples of control effectors, and they all have their individual dynamics. They're not instantaneously acting. So we can model those within CLASP. We can visualize the flight of the aircraft by an interface with Flight Gear Flight Simulator. We'll see some examples of that later on. We have the ability to do closed loop simulation, so with the controllers active. We use rigid body equations of motion, 6DOF, about the mean axes, and we use the mean axes because that allows us to use modal approximation for the structural dynamics. And at the core of this, we have the aeropropulsive characteristics of the aircraft, which are derived from flight stream analyses and which then get incorporated within the CLASP framework, either as lookup tables or embedded analyses or reduced order models of some sort.
Yeah, okay. So without getting into too much detail, I'll just make a few comments about this gust modeling capability. We have a complex looking little diagram here, but the part about flight stream is shown in the orange boxes here. So where we interact with the CLASP functionality. But basically with flight stream, we have the geometry coming in with control effectors and propulsors. We put in whatever position orientation is required, then we run through an unsteady solver and look at the evolved loads, and we're able to then output the loads to the 6DOF. So we'll close the loop by going back through the time-dependent boundary and the time-dependent weight evolution, reposition the geometry, do the unsteady solver again. So and then the output interacts with the Amon's CLASP tool here. So we'll go to the next slide. Yeah, so this kind of just gives you a little bit of an idea about what we did in the phase one. We had a flight stream reducing the order of the aero to a reduced order strip type model, and Mon will talk a little bit about that. We have a prototype aero propulsive model, axial flow rotors, and a 2D gust model. The CLASP framework then has been worked out for forward flight, and we're doing a prototype CLASP structural dynamics model and then, of course, we have prepared a report, which we presented that just last week. So this is basically the report on all of our activities. So next slide, I'm on. In order to be able to do this problem, we had to put in motion definition. And this slide just describes a little bit about the motion definition capabilities we've added to FlightStream. We've got standard translation and rotation velocities, but also custom motion tables, and 6-DOF integration with some additional motion capability there. So we can talk a lot more about that offline, but we do have an unsteady solver. It's unsteady at the surface, and we have unsteady loads that we're able to generate with rotating propellers. And so this kind of forms the foundation of what we're doing with this gust modeling. I won't get into too much detail there with exactly all the details of the unsteady solver, but just this is just illustrating our capability to do both 6-DOF type motion and propeller blade rotation with the effects on the wings there. All right, yeah, so the initial gust model is just this 1 minus cosine kind of simplified approach. This was just to get something in for phase 1 that would work and would be reasonable. So we have user-defined gradients, and the gust velocity variation in FlightStream is time-based and coupled to the unsteady solver. And the atmosphere is assumed to be one-dimensional in this first approach. And so you can see in this slide what these gust models actually look like. This is really just applied to the function for some different input conditions. Okay. Of course, in our STTR reporting, we have to talk about the technical merit, and FlightStream basically allows for the rapid analysis of unconventional aircraft using this unique capability for surface vorticity solving and flow separation with some viscous effects added. So it's kind of a middle of the road in terms of fidelity, but it offers the speed required to actually approach this gust modeling problem. I'm going to give Aman a chance to talk a little bit more about the gust definition when he gets to his slide. So, yeah, there we go. So the gust encounter problem is just illustrated here in this little video. You can see what happens over here to the load as the gust goes over the airplane. So this is basically just a time-dependent evolution of the gust passing over an airplane in forward flight. Okay. All right, so this reduced order model essentially reduces, in order for us to be able to interact with Aman's clasp tool, we reduce all the aero to, in this case, a quarter chord imposition of loads along the wing. This allows us to go to a strip model and interact with the flight dynamics software and simplified models. And this is kind of a novel approach that we've decided to take with this particular project, because basically what the whole idea here is, it allows us to get better fidelity loads than you could get with vortex lattice, but still apply the loads in the same way you would apply the loads as if they had come from a vortex lattice tool. All right, Aman. So this is just some examples of some reduced order model loads that we've gotten from the LE8. Okay, Aman. All right. So to do the air analysis and flight gear, Aman, you may want to talk a little bit more about this, but basically we were able to generate an OpenVSP model and put it into FlightStream, get the loads, and then Aman was able to take clasp and interact with flight gear. So did you want to say anything else about this one, Aman?
Nope. I can just step in here. So
yeah.
So what we've got is we've got a couple of different ways we're using geometry in this project. And so the starting point is an OpenVSP model that you see over here. And the top track is that OpenVSP model then gets exported and then brought into FlightStream. which is where we do the error propulsive analyses and generate either lookup tables or whatever other type of reduced order model we're going to be using. And then those characteristics get embedded within the CLASP Simulink framework, which we're going to look at in more detail. The other track, mostly for the flight simulation and visualization track, is the same OpenVSP model gets exported into AC3D, which is a geometry rendering tool, and we create a flight gear aircraft model for flight gear flight simulator. And when CLASP Simulink model operates, it actually pushes data and interfaces with the flight gear flight simulator, and that provides us a visual rendering of the flight and trajectory of the aircraft. So now let's talk. I'm going to talk a little bit about how we've modeled the flight dynamics and the structural dynamics of the aircraft within CLASP. So as Roy alluded to previously, we use a strip theory-based aerodynamics model, air propulsive model. So the idea is that the lifting surfaces on the aircraft, and for phase one, we've just concentrated this to the fore and aft wings. We look at the aerodynamic loads as a buildup of loads over a large number of span-wise strips on these wings. And at each of these strips, we can compute what the local incidence angle seen by that strip is by looking at the gross motion of the airplane, so its attitude relative to the oncoming free stream, any angular rates like roll, pitch, yaw rates that it has, the geometric location of where those strips are, as well as the effects of downwash, and also if there's any structural deformation going on, then that's going to create a normal component of velocity seen by the strip as well. Also, as Roy alluded to, then what happens is using the strip theory-based model, sectional loads are basically originate at the quarter chord point of these strip airfoils. And depending on where that quarter chord point is, we then sum up the loads and moments relative to the aircraft's moment reference center. So that, in a nutshell, is how the strip theory-based model works. So in phase one of this effort, we've focused on forward flight conditions, and we haven't looked in great detail at the effect of prop wash going over the wing. So those are all activities that we've got lined up if we have a phase two funded. And we also want to have a tighter integration between the reduced order model that Roy mentioned that would come out of flight stream and then directly integrate into CLASP. So here's a top-level overview of the CLASP framework, the Controls and Load Alleviation Simulation Platform. So this is a Simulink model, and this is the top level of that model. We have in this sensor models block models for the dynamics of sensors. So the difference between a true state and a sensed state as sensed by the sensor. So obviously, these sensors have their own dynamics, probably bias or any noise. So those things we can model within this block. So flight control system, FCS, and gust load alleviation, GLA. So the control laws for closed loop control of the vehicle, those are all modeled within here, and there's great flexibility as to the type of controllers that are modeled. And we'll see some examples of what we've incorporated for our phase one. Between a control command being generated and a control effector assuming a particular state, there's, of course, the dynamics of the control effectors, which we can also model by anything starting from a first-order dynamic to a second-order dynamic or anything even more customized than that. So these are all possible within the control effector dynamics block. We have a fairly robust way of defining how the atmosphere itself is moving. So the ability to program in winds and gusts and turbulence. This is something we have in this atmosphere block. The main block, basically the heart of the CLASP framework, of course, is where the air propulsive loads and structural deformations are summed up. And once we have the gross loads over the entire body, we integrate the equations of motion to kind of compute the time history of the trajectory of the body. And because we use the mean axes as the vehicle deforms, the center of gravity of the vehicle will also move. You imagine the wings bending. That's going to result in a movement of the center of gravity. And the mean axis approach requires that the position of the center of gravity is tracked for the rigid body equations of motion. And then finally, we have, as I mentioned, this output to flight gear flight simulator that allows us to see a visual rendering of the motion. So now I'll talk a little bit about the gust alleviation algorithm we've got implemented right now.
Hey,
So,
Mon, if I could pause you for just
yes.
a moment. We have several questions here in the Q&A.
Oh, really?
And, before we continue on, so regarding the Simulink control system model, is that open source or is that all controlled and owned by Flight Research and Flight?
Well, it's very much in the development stages right now, the CLASP framework. It is something that we ultimately plan on commercializing. So the end goal is it would be available as a commercial tool, just like FlightStream is.
All right, understood. And could you elaborate on the type of controller that was implemented within this algorithm?
Absolutely. Actually, I was going to walk through that in the following slides.
Wonderful, wonderful. Another couple questions, just very briefly. Can the derivatives and the lookup tables mentioned in the MATLAB 6DOF model be reliably extracted from OpenVSP, or do you rely on FlightStream for that?
We rely on FlightStream for the aerodynamic analyses that generate the lookup tables.
Wonderful. And now we've got a question here that says, it looks like FlightStream assumes a rigid structure. Can it also work with a flexible structure, or is it all rigid body?
Yeah, no, I can answer that. Yeah, of course, it's the steady solver assumes a rigid body, but we do have an unsteady solver that is able to do the non-rigid structure problem.
Wonderful. Thank you very much for answering those questions, and I'll go ahead and mute, and you proceed. Thank you so much.
Okay, so since we had a question, let's talk about the gustal alleviation. So imagine there's a vane at the nose of the aircraft which picks up angle of attack. The thing to note is because there's an offset between the airplane reference point, you can think of it as a CG, and the vane, the angle of attack that's being picked up by the vane is also affected by any angular motions of the aircraft. So we're able to model within CLASP what the angle of attack sensed by the vane is as a function of where the vane is located and the motion of the aircraft. And then obviously, since this angle of attack vane is bound to have dynamics of its own, we can represent the dynamics of that sensor in as simplified or as complicated a manner as we want. So there can be n number of sensor states. And then the gust alleviation algorithm, of course, we don't want it to respond to the total sensed alpha. We want it to respond only to the gust-induced angle of attack. So there is a way to extract then the gust-induced angle of attack from the total angle of attack seen by the vane. Now, there are two ways of looking at this, and that depends on whether we assume that there's a change in the gust field velocity over the dimension of the vehicle. So if you imagine, is the velocity of the gust changing over this length of the vehicle? If the answer to that is no, then we can just calculate the angle of attack at the vane based on the relative location of the vane relative to the reference point where the aircraft motion states are calculated. On the other hand, if you have a velocity field where there is appreciable variation of velocity between any 2 points on the vehicle at the same time, then as we'll see later, what we can do is we can just add the position of this angle of attack sensor to a list of query points which are used to query the state of the atmosphere, so we can get the velocities over here directly. So I mentioned about the sensor dynamics over there, and this is how we can extract the gust-induced contribution to the angle of attack from the total angle of attack picked up by the vane. And without going into the details of this equation, the way this is done is you basically subtract out the components to angle of attack due to the rigid body motion of the aircraft. And when you subtract that from the total angle of attack, you end up with the gust-induced contribution. And that's what the gustal alleviation algorithm will respond to. So there's also a question about the flight controls architecture. So here's what we've implemented for now. Our focus has been mainly on longitudinal dynamics with vertical gusts. So if you look at the top track over here, we have an altitude hold autopilot, which is trying to maintain a commanded altitude. And based on the error in altitude, it's developing a pitch attitude command. And there's a pitch hold controller and pitch damper, which is basically attaining that pitch angle command by basically moving the elevons of the LA8 configuration. So that's one signal in the longitudinal channel. The other one is the GLA controller. So the GLA controller is exercising PD, or proportional derivative control, based on the gust-induced angle of attack. And it's trying to keep that gust-induced angle of attack to a 0, so counteracting it. And that's also adding to the longitudinal channel. So these two controllers, they're basically summing on top of one another and generating the elevon command, or the longitudinal control command. And on the lateral side, we just have whatever we would need to keep the wings level. So we have a wing leveler or a bank hold. And not shown on this image, there's also a yaw damper, which will prevent any kind of Dutch roll excitation. Now I'll talk a little bit about wind, gust, and turbulence models. So this is actually a dedicated block or subsystem within CLASP. And we have a number of ways we can make the atmosphere move in here. So there are already horizontal wind and von Karman turbulence models that are available as part of Simulink's aerospace block set. So those are in here, and they work just fine. The only thing to remember is that they are generating gross movement of the atmosphere. You can't have any variation between 2 points on the airplane at the same time. But we anticipate that for our specific problem, we're going to have plenty of cases where the wind velocity changes over the span of the body. So we have this user-defined velocity field as well. And here, the user would have full freedom to define velocity components as a function of x, y, z, and t. So basically, spatiotemporal variations of the velocity field can be defined here. And any number of points on the vehicle, the locations of those points can be used to query that velocity field and see what the velocities are seen by those points. So query points in our case would be all the aerodynamic centers of all the strips on the vehicle, as well as the locations of any air data probes on the vehicle. So we would want to query the velocities seen by each of these points because they factor into various calculations downstream. So now for the air propulsive and structural loads, basically here's what's happening. So obviously, in order to calculate deflections of the body, we need to have the distributed loads over the flexible structures. And with those flexible loads, we have a modal approximation-based structural dynamics model that can compute the deformed state of the wings. So the wings have degrees of freedom in bending and torsion. So we can compute the bending and torsion states of each of the wings, as well as the rates at which those states are changing. And this information is then propagated to the air propulsive block, which is the blue block that you see over here. The important thing to note over here is obviously in early simulations, we might want to just simulate rigid body motion. So this entire block can be deactivated, and that with one click, and that basically makes the whole airplane a rigid body. Now with that, with the instantaneous structural deformed state of the structure, the strip theory model then calculates the loads that are developed on the airplane, and those loads are first of all summed up to get the gross vehicle loads, forces and moments, and those quantities go to the equations of motion. The other thing that goes to equations of motion would be angular momenta of all spinning rotors and propellers on the aircraft. So if there's an angular momentum imbalance over the aircraft, and if you couple that with the rate of the aircraft, you're going to get a gyroscopic moment. So we propagate that as well. So the equations of motion are affected by any such moments if they're there. The same loads in a distributed manner get put into a load matrix, which has basically the distribution of bending and torsion loads over all the flexible structures, and that goes right back into the structural dynamics block to compute the new deformed state. So this is happening at every time step of the simulation. The structural dynamics modeling that we've got so far for phase one assumes that the only flexible components on the aircraft are the four wings, and they're modeled as cantilever box beams. So they're rigidly fixed at one end, and they're cantilever free at the other end. And they have degrees of freedom in bending in the lift direction, if you will, and also torsion in the twist direction. And for phase one, we've assumed that the bending and torsion modes are uncoupled, and it's just a simplification made to do an initial implementation. We've sized the box beam based on a small optimization problem. So it's basically, if you assume that the leading and trailing edges are at fixed locations, how thick do you need to make the box beam in order to satisfy a tip deflection and a tip twist constraint, as well as lower bounds on first bending and first torsion frequencies, subject to a certain NG load condition. So that's solved as a small pre-processing optimization problem. And once that problem is solved, we get the bending and torsion mode frequencies as well as mode shapes. So you see the bottom right, the first three mode shapes for bending and torsion, as well as the frequencies for bending and torsion modes. These all get embedded into our structural dynamics model. And the way we calculate the deformed shape of the wings as a function of time is by a modal approximation method. So what that does is it evaluates the physical deflected state as a truncated summation of those mode shapes that you saw, along with generalized coordinates representing bending and torsion. And the user has freedom over how many modes of that infinite summation the user wants to keep before chopping off the sum and truncating it. So within the structural dynamics module, so we have these distributed loads that come in. And if you have structural modes in bending and torsion whose frequencies are close enough to the rigid body frequencies that you want to actually integrate them together with the rigid body motion, then that can be done. So here you have actual time integration of bending and torsion modes whose frequencies are relatively low. If, on the other hand, you have bending and torsion modes whose frequencies are high, then what that basically means is that as far as the rigid body motion of the aircraft is concerned, relative to that, those particular modes are always in quasi-static equilibrium. So then we don't bother with time domain integration, and we just propagate the quasi-static deflections directly. So in a typical problem, the lower few modes will be time integrated, and higher frequency modes will just have the quasi-static contributions. And finally, the modal coordinates are abstract coordinates. They have to be converted back into physical coordinates, so things we can visualize, like a bending deflection or a torsional twist, and the rates at which these deflections are happening. And these will then get output to air propulsive and mass properties modules. One interesting thing we had to figure out was, how do we trim this flexible airplane? And not only how do we trim it without having to change the setup of the trim problem if we decide to switch the structural dynamic stuff off and do a rigid body simulation. So the flowchart on the right shows what we ultimately came up with. So you have the trim algorithm is actually an optimizer. The reason we've set it up as an optimizer and not a root solver is because we totally foresee trim for these UAM type vehicles as being I mean, these are all over-actuated systems. So there are far greater number of control knobs than the degrees of motion freedom of the body. So in the general cases, there will be more than one unique trim solution. So to choose among them, we have to minimize some kind of an objective function. So that's why trim is set up as a optimization problem. And the optimizer is basically passing down trial solutions of control and state variables. So control variables, you can imagine, would be control deflections or propulsor RPMs or blade pitch, and state variables would be angles of attack, angle of side slip, and so on. And for each such trial solution, we first iterate the aerodynamics and the structural dynamics to an internal convergence. So think of it as exposing the aircraft to the airstream and letting the flexible structure blow itself into an equilibrated state. And then once that internal convergence has happened, we then go and check whether the 6 degree of freedom equations of motion are satisfied. So is there dynamic equilibrium there? And any other state residuals, if applicable, are they satisfied? And then what is the value of the objective function for trim? And then these are fed back to the optimizer, which then goes through this process again, trying to minimize the objective function. So the advantage of this is at a click, you can just turn this off. And then you're basically solving the rigid body trim problem. And the optimizer doesn't really care whether it's trimming a flexible or a rigid airplane. Okay, so now we just look at a couple of quick results. And we've simulated a symmetric gust encounter, so longitudinal motion only. We've simulated an asymmetric gust encounter, which is basically just one half of the airplane. So just imagine the right wings encountering a gust and nothing happening to the left wings. And then turbulence. Okay, so here's a symmetric gust encounter simulated by CLASP. So there you see the wings deforming as the gust hits first the front wing and then the aft wing, and you can see control surface deflections as the controllers try to counteract the effect of the gust. So just to set up a baseline case, if you look at the dotted black line, that's what would happen if the vehicle got hit by the gust and took no control action. So it's an open loop controls fixed case. And what you see, of course, here is the beginning of a phugoid cycle. So if we had simulated this for 100 or 200 seconds, you'd have seen a phugoid cycle developing over there. But that's just a reference case. The blue line is what would happen if you had an altitude hold autopilot on without any gust load alleviation system. So the first thing you see is that controller works the altitude back to the equilibrium altitude. So it prevents the excursion in altitude, but it doesn't really do much for the load factor. So if you look at the peak load factor on the positive side between the black line and the blue line, shaves a little bit off, but not much. That's because it's responding to change in altitude, not change in angle of attack. If you look at the red line, that's the effect of the gust load alleviation system being on top of the flight control system. And if you look at the angle of attack excursion for this red line, you'll see that the angle of attack seen by the vehicle, the change in angle of attack is a lot smaller. That's because the gust load alleviation algorithm has been counteracting the gust-induced angle of attack. So the angle of attack peak is a lot lower. Angle of attack directly related to the amount of excess lift, which is directly related to the load factor. And as a result, you see the peak load factor here is lower, but at the same time, the control action taken is a lot more aggressive. So if you look at the red control input for the elevons versus the blue control input, that's a lot more aggressive. So this is just a proof of concept. Can we see the difference between these three different simulations? Another interesting thing is that once this vehicle flies into the gust, obviously there's a finite length of the vehicle and a shape of the gust. The front and aft lifting surfaces sample different velocities at the same instance in time. And this is called the gust penetration effect. In the earlier part of our work, when we just used static lookup tables, we were just querying alpha, one single alpha for the whole vehicle. So we couldn't really capture this gust penetration effect. So when we did that same gust encounter back then, you see the moment the vehicle encounters the gust, it pitches down. Intuitively, you'd think as this wing enters the gust, the vehicle will pitch up first. And then as both wings enter the gust, static stability will take over and then the vehicle will pitch down. But if you don't take into account the gust penetration effect, you can't capture that pitch up. With our strict theory-based model now, there's the pitch up. And this is when the front wing has entered the gust, but the back wing has not. And so the vehicle is pitching up, and then the pitch down happens as both wings get into the gust field and static pitch stability begins to show its effect. Okay, here's an example of an asymmetric gust. Only right wing gets hit. So the lateral controllers come into play over there in trying to stabilize the bank angle of the aircraft. And this is just an expanded view of the deflection and the twist of the tips of all four wings when it encounters the gust. So it sets up a structural dynamic, and then that dies down after some time. The final thing is a turbulence simulation. This is just using the von Karman turbulence model that's part of Simulink. So basically turn on the turbulence and turn off the turbulence as you please. And then you can see how the vehicle responds to that turbulence field. So the control action is a little bit difficult to see because they're small, but the elevons are being deflected by the control system to try to counteract the turbulence. And the severity of turbulence, of course, can be varied as well. So to summarize, we've got our belief is we've got a reasonably good proof of concept setup of the CLASP environment and getting information from FlightStream. And if we get funding for phase 2 of our work, this is going to be our launching point, and we're going to add capabilities, and most importantly, for vertical flight mode. All our work has been forward flight in this phase. So our top priority for funded phase 2, if it's funded, is vertical flight mode for UAM type vehicles. Okay, that's it from Roy and me today. If there are any questions, be happy to take those.
Thank you very much.
Thank
really
you very
interesting
much.
information. Oh, there's an echo coming through somewhere. Is someone got the live stream open?
Hey, Brandon, I'll just mention real quick. You notice our website and my email address up there. If anybody has any follow-on questions later on, we'll be happy to put you in touch with them on or try to answer the questions related to FlightStream.
There are actually a couple more questions on the on the IO page. The first one is, what type of lookup tables are you grabbing from FlightStream, i.e. aero tables, propulsion, etc.? Can you also grab them in OpenVSP for comparison as well? And if yes, can you show a demo?
Yep, I'll be happy to answer that. Let me just go back to a slide that helps me answer that a little bit better. So in our this slide right here. So in our strip theory based model, we basically, so only the lifting surfaces are analyzed using strip theory. So for the rest of the airplane, so if you look at the fuselage and the vertical fins, which are considered to be rigid, we've basically run FlightStream. We've run the whole geometry in FlightStream, and then we've created static lookup tables for the assumed rigid part of the geometry. So the fuselage and the effects of the fins, those are basically lookup tables for the 3 force components and the 3 moment components as a function of alpha, beta, and rates. And the strip theory model is for the flexible part of the vehicle. So the 4 wings, those are strip theory. The implementation is general to the point where, provided the lookup tables are in a particular format, like Z is a function of XY type of format, it's insensitive to whether that comes out of FlightStream or whether that comes out of any other aerodynamic analysis tool. And this was actually one of the starting goals of the CLASP environment was it should not be married to any one source of aerodynamic data. So yes, if there's analysis coming out of VSP Aero, I think that was the question, then yes, if we just have to get the lookup table into the agreeable format, and then we would be able to do the simulation. We do not have a demo of that at the moment, but this is something we could definitely pursue in the future.
Okay, we had I'm going to jump back and forth over to the YouTube. Does the swirl from the propulsors impact the forces generated by the controls?
In phase 1 modeling, to the extent of phase 1 modeling, no. And the integration between, the interaction between aero and propulsion, this is one of the main targets of phase 2 if it's funded.
Okay. How does CLASP ensure that there's no unintentional phugoids setting in, or an automated version of PIO, pilot-induced oscillation?
The phugoid will have a time period that is large enough that the moment you put the altitude hold controller in the loop, that automatically will knock out the phugoid. So the time period for the phugoid is going to be 20 seconds plus, probably. And so the moment you put the moment you close the loop around this vehicle, phugoid tendencies are going to go away. So a phugoid might be excited if there's a gust encounter, but it will be killed pretty quickly, as you saw in the simulations. PIO is, to study PIO, we would have to put a mathematical model of the human pilot. So far, we've just done flight control systems. We would then have to put a mathematical model of the human pilot, which then commands the flight control system, which then commands the control surfaces. And then we'd be able to study PIO. This is not something we've done within phase 1. So there's no real result to show for it yet.
Okay. And then the last question that's up so far. Oh, here another one just came. But how did you model the propulsors and the batteries and the electric propulsion system? I think is what they're really asking.
Got it. So let's take that from the tail end. Batteries. Modeling battery or the state of the propulsion, the state of the energy systems, that's not really within the scope of this particular project. This project is more about flight dynamics and the trajectory of the aircraft. So there's no modeling of batteries or their discharge rates within the scope of this project. The other question was, I think it was it?
Just the rest of the propulsion system, and I think the answer is that you just started at the propeller or the disc, and you ignore everything that's the disc is turning, the propellers are turning, and that's the way it is.
Yes, and phase 2 will see, say, a blown wing with an aft control surface, with a trailing edge control surface, which is deflected. So obviously, that's going to be the response is going to be dominated by the amount of blowing you've got over the wing, and those are all phase 2 action items that we're really going to stress on if funded. Yes.
And then, is the mass properties model coming from OpenVSP?
The mass properties model is at the moment not coming from OpenVSP. What we've done for phase 1 work is so the LA8 is a wind tunnel scale model, so smaller aircraft. We've scaled it up to about a 6.5 meter wingspan. Basically kind of wingspan that you might expect for a 1 or 2 passenger UAM. And we've scaled up the mass properties accordingly based on just first order principles, mass. So the mass and the inertia tensor, those got scaled up or estimated based on first principles. And the CG, we've located it based on information we had about CG location from the Langley folks for their wind tunnel model. So these are not coming from OpenVSP at the moment, but there's no reason why they can't.
Okay, I think that's all the questions that have been posted online so far. If you guys have any more comments, you're welcome to. Otherwise, thank you very much. I'll let Brandon go from there.
Yeah, thank you very much. Really great work, and really appreciate your time this morning. For everyone online, we have about 8 minutes or so before our next presentation by Garrett Klunk from ES Aero on demonstration of autonomous differential throttle-based flight controls. So what we're going to do is just go in standby for just a few minutes, and right at noon we are going to start that talk. So thank you all very much for participating. Thank you for your presentations, and we'll see you in just a little while. All right, everybody, it's 12 o'clock. We're going to go ahead and move things along and open up to Garrett Klunk from ES Aero presenting some work with UIUC. And let me drag this window over here and go full screen. Garrett, if you like, it's all yours.
Thank you very much. As Brandon said, I'm Garrett Klunk, and today I'm going to be presenting a status update to an ongoing NASA Phase 2 STTR program between ES Aero and the University of Illinois at Urbana-Champaign concerning the development of an autonomous flight controller for a subscale distributed electric propulsion aircraft with a focus on how we are using OpenVSP and VSP Aero to support validation and verification efforts under the program. With that, before we begin, I'd like to provide a brief review of the program background. So the goal of this NASA STTR Phase 2 is to develop a reconfigurable autonomous flight controller for a distributed electric propulsion aircraft, not only to provide lateral and longitudinal autonomous controls, but also to be reconfigurable in the event of failed propulsors. What's also unique about this is the propulsors themselves will be used as control effectors in addition to conventional aerodynamic control surfaces. And so the controller will reconfigure around propulsors that are inoperable to still maintain effective control. And what we'll be focusing on today is the comparison of our estimation of flight dynamics with OpenVSP and the system identified flight dynamics from our flight testing campaign of the subscale vehicle. On the VSP Aero side of things, last year, one of our engineers, Nick Brake, presented a status update on this program, detailing how we modeled our ducted propulsors in VSP, our development of a DEP array custom component to ease the modeling process of those propulsors geometrically, and our initial vehicle characterization, including propulsion airframe interactions using VSP Aero. And what we'll be talking primarily about today is our initial comparisons of those dynamics estimated in VSP Aero to flight test data and system identified flight dynamics. And with that, I will dive right into how we're modeling our aircraft dynamically and our comparison between VSP Aero and flight test. So to begin, we start off with standard textbook longitudinal and lateral directional aircraft dynamics systems of equations in 6 degrees of freedom motion, and they are presented here in state space form. We have a handful of stability and control derivatives for the baseline aircraft with control surfaces that can be estimated by use of VSP Aero and the automatic stability calculation subroutine within it. And for reference, I also provide our axis system, which will be relevant to keep in mind for later for positive forces, moments, and control surface deflections. From that baseline 6-DOF modeling, we also wanted to capture the influence of propulsors on the aircraft dynamics as well as control. So in order to do this, we characterized the propulsor used on the subscale flight test vehicle using X-rotor to build a aero performance map. And essentially, we replicated the linearization process from VSP Aero manually using this flight test data. So we were interested in performing a linearization about difference in thrust. So using the X-rotor data, we correlated that to a difference in RPM at our flight condition, and then use that delta in RPM to gather thrust and power coefficients from the propulsor data, and used those settings as inputs to the rotor disk element settings for the rotor disk components in VSP Aero. And what that allowed us to do is to run two different flight conditions to produce that delta, and then linearized forces and moments about those to get the stability derivatives, quote unquote, for the propulsors shown in green. What we also did was we assumed that there was going to be some propulsor dynamics in the physical response of the propulsor itself to its commanded signal. And we represented that with a first order transfer function based on prior efforts in the end of the phase 1 program and the very beginning of the phase 2. And from here, want to take a look at how we're using VSP Aero for this. So we started off by using the simplest solver, the vortex lattice method steady solver, with the geometry observed above. And for this, it was a really fast and computationally efficient method for generating aero forces and moments, and is generally effective for very simple planform geometries like our conventional Cirrus SR22 model. And it also had the benefit of being able to use that subroutine for calculating stability and control coefficients for using estimating derivatives. But while we were working on that, the unsteady solver came out, and we decided that we also wanted to explore that for producing similar data sets, primarily because we were interested in what might have been a more representative propulsor behavior rather than the rotor disks used in the steady solver. However, we quickly found out, due to the very high RPM of the propulsors compared against the very low velocity of the aircraft, it became a very slow and computationally heavy process. And we also required to do the manual linearization process across all states and control variables for our dynamics model using the unsteady solver, because it's simply not built for that stability calculation subroutine. With all that in mind, our goal for looking into VSP Aero in the first place is to see whether or not this approach is sufficient for controller development in place of a high resource cost source of data, such as a flight testing campaign. Could you get close enough from the comfort of your own laptop? And so with that, it warrants an exploration of the data that we are comparing against. So what we're seeing here is a very high-level summary of what UIUC has done for supplying the system-identified data set for us to compare to. More details can be found in Aaron Perry's PhD dissertation, referenced in the bottom right of this slide for anybody who's interested. But as a brief overview, not only did UIUC perform a scope of flight testing with multi-orthogonal multi-sign maneuvers, exciting various dynamic frequencies of the flight test vehicle, to generate a set of flight test data used in the system identification process to identify stability and control derivatives, but also performed a suite of wind tunnel testing of a subscale version of the subscale aircraft to look into general trends that we might expect in forces and moments from varying installed propulsor thrust. On the bottom left side of the slide, you can see a comparison of the raw flight test data shown in black traces and the reconstructed data, maneuver data from the system identified dynamics model produced from the system identification process. And in general, it is very close, but there are some differences that lead to some drifting in the response, which is typically expected and often requires a lot more training of the model to get more closely aligned. With that, I'd like to dive into the beginning of our comparisons of these models. So the first step in comparing the models is the model architecture itself. The system of equations that underpin the estimation methods between VSP Aero and system identification are largely similar but differ in important ways. The primary way in which they differ is the definition of propulsor contributions to the flight dynamics. As I mentioned before, with our VSP Aero approach, we are looking at differences in thrust input with a propulsor dynamics model included for an actuated response in the aircraft dynamics. But in the system identification model, the flight test data extracted from the flight test campaign really can only trace throttle input. It's very difficult to get beyond throttle from and connect the dots between throttle and thrust. So in addition to that, there are no propulsor dynamics included. There's an assumption that they may not be significant enough to warrant inclusion in the dynamics here. So those differences are hard to bridge across the gap. However, the set of pure aircraft dynamics highlighted in red should be directly comparable as they follow the same form. And in addition to looking at the models themselves, we have to reconcile the concept of what is actually happening when we linearize or attempt to linearize forces and moments between the two approaches. And this really was probably is the largest takeaway from our work thus far, where in VSP Aero, you can set the vehicle to a specific trim flight condition and run analysis on that. And then if you want to look at how forces and moments change with a deflection of the elevator and positive elevator deflection as shown, you can do so while keeping the vehicle parametrically locked so that you're holding all other parameters constant, same airspeed, same angle of attack, etc. And this allows for a more decoupled analysis of each state and control parameter to narrow in on their specific contributions to dynamics. And this is most similar in the physical testing environment to a wind tunnel test on a fixed sting, where you can hold the vehicle in a flight condition and perform these tests. In the system identification side of things, even though the equations of motion which underpin the analysis are very similar, the vehicle is flying and therefore is able to react to perturbations of control vectors. So with our example, again, if you're at a trim flight condition, and you deflect the elevator, you will have a very quick response which changes other state parameters such as airspeed, angle of attack, nose down pitch rate, and attitude, which um, will continue to change throughout time very quickly, and you find yourself in a different dynamic state um, than you were before. And that the challenge that introduces is when you have very similar terms, um, building out the equations of motion in state space form with different stability derivatives, it becomes difficult to determine whether the change in forces and moments should be attributed to the control deflection which you enacted or the immediate changes to the other states which followed from that. So what this does is kind of muddies the water from an apples to apples comparison to something different. And this is what we see when we examine each stability and control derivative in both of the models with our various approaches. So what you're seeing here is a visual representation of that comparison with scaled down versions of each stability and control parameter. This slide for longitudinal dynamics, comparing system identification results with error bars and vortex lattice method steady and unsteady approaches. And on the whole here, we see either outside of the assumed values with the gray boxes, we see either approximate matches or poor matches in the dynamic variables. And we can dive into some of these pretty quick. The first being force of in X due to air changes in airspeed. That's largely a drag estimate, and it is known in the VSP community that the vortex lattice method has within itself a very rudimentary estimate for parasite drag, and there are better ways to estimate that even within OpenVSP using the parasite drag tool to get a better idea of that characteristic. So that might help explain some of the differences there. The discussion I had in the last slide about how the vehicle reacts to changes in elevator deflection make themselves more relevant here with each of those derivatives, where not only are we seeing large differences in magnitude, but we're also seeing changes in sign between them, which very well could mean the difference between if this were used in an autonomous controller as the state estimator, it could mean the difference between a controller which stabilizes an aircraft and a controller which destabilizes it based on that sign convention, which is very important to note. And we also see instances where the system identification estimates are so close to zero that they're uncertain, the uncertainty bounds around them cross zero and could land on either side of positive or negative. And so with those, we're really not sure what we should be comparing against. But in those instances, tools like VSP Aero can help inform the end user of what side of the line perhaps they should be. And as we look at the lateral directional case, this is the same comparison just with the lateral directional dynamics. We see similar things pop up. We see a lot more instances where the uncertainty bounds on our system identification are wide enough to where we're not entirely sure what side of the sign they should be on. But again, VSP Aero can help inform what those should be. And I think it's most represented here with the y force with respect to elevator deflection, the fifth from the left. But outside of the other results, there's another which we point out, which is the yaw moment due to side slip derivative, which also doesn't match what system identification produces. And if you've been astute in the previous slide, you might have noticed that all of our VSP Aero simulations have been run without the fuselage included. And this is because while we modeled it early on, while we modeled it as accurately to the flight test vehicle as we could, we had some modeling troubles that were not easy to resolve with that geometry, and so we omitted them, believing that omitted the fuselage, believing that at the scale at which we were working with for this vehicle, we may not see a large effect on the overall dynamics anyway. However, on larger full-scale aircraft, it is well known that the fuselage provides a destabilizing effect on the N beta term specifically, which, if applied here, could bring the vortex lattice method estimates down towards where the system identification method prescribes it probably should be. So there are some conclusions about how we're modeling the aircraft in OpenVSP and VSP Aero, which system identification can shed some light on as well. But again, this is all fairly work in progress. So a summary of our key takeaways here of our current progress is that most of the VSP Aero stability and control derivatives that we've seen do appear within similar orders of magnitude of identified derivatives, even if they're not exact matches. A lot of them are approximate matches in that way, which is fairly encouraging and suggests that while it suggests that those estimates can likely be used for static and dynamic stability analysis at the conceptual design level within similar orders of magnitude, where your estimates are approximate and quick results are desired for quick iteration on designs. However, the differences that we do observe may come from the fundamental differences in how the flight conditions are modeled between the two approaches, whether they're fixed and allow single perturbations or single perturbations affecting a dynamic response, such as in flight. Those may contribute to a lot of the differences we're seeing in the stability and control derivatives, and may limit the use case for VSP Aero for controller development as a result. And we also, for our specific use case, found that the unsteady solver in VSP Aero might not be an ideal tool for us to pursue stability and control derivative estimation for. As I had mentioned before, the vast difference in the RPM of our propulsors against the relatively slow airspeed makes makes an unsteady solution for which encapsulates a fully developed wake over the entire vehicle geometry, really time consuming, on the order of days. And on top of that, having to run a case to perform manual linearizations about each state and control parameter make that a very time-consuming process. However, that's not to knock the tool for anything. It may not just be designed for that purpose. It has its uses, but for something this time-consuming, it may not be appropriate. And from that, we have some next steps that we really need to address for our work. The first of which being to reintroduce the fuselage back into the analysis, maybe with a simpler geometry that represents the general shape of the fuselage, to see if we can correct some of those derivatives that are known to have notable effects from the fuselage itself. And then while we say that the unsteady solver might not be ideal for a full stability and controls analysis, we can still look at point cases by running a fully developed unsteady case at the baseline trim condition to compare results from steady and unsteady and what that might tell us for our accuracy there, and provide a more complete comparison of relative performance versus resource cost. We also want to take a look at the VSP aero and system identification estimates for propulsion airframe interactions and their effects. This may require converging the underlying dynamics models between the two approaches around propulsor parameters that can be tracked between both methods. The challenge being how we connect installed thrust on the flight vehicle to throttle, which is something that we can directly measure, and how we navigate that gap. And then, of course, a more traditional comparison of the dynamics models as they're all built up in subjecting them in an environment like Simulink to specific input maneuvers and assessing their response traces to see, the comparison that we've done so far has been great for giving an indication of what specific derivatives are comparable versus not, but it doesn't give a great idea of how different parameters, I guess, how sensitive they are to those differences, how much of a difference matters for a vehicle like this. So those being our next steps, at this point, I would like to thank you for listening in on my presentation and open the floor for any questions.
Great, thanks, Garrett. Looking at the live stream and the conference IO session, doesn't look like anyone has anything at the moment, but everyone listening in, please feel free to ask now if you have any. Otherwise, great presentation, and thank you for sharing.
Yeah, I really appreciate the time, Garrett, and it's good to see some of the work going on in my alma mater. So for everyone listening in online, we've got about 3 minutes until Justin starts with his presentation on building the OpenVSP program from the source code. So we are going to take a very brief break and then
Hold on
come
just
back.
a second, Brandon.
Oh, hang on. There's Rob.
I have a question.
Certainly.
Thanks, Garrett, for the talk. I think you make a really good observation about the discrepancy in timescales between what it takes to resolve an actual rotating propeller versus the dynamics of an airplane. And I've seen this also, well, I'm just talking in terms of computational cost, yeah. And then I've seen this also when people think that they're going to model a tilt weighing through transition from start of transition to end, but then resolving time accurate rotating blades the entire time. And you just think about that, a transition from beginning to end of a VTOL vehicle may take a minute. And if your props are at, several hundred RPM, then you're going to need to model several hundred revolutions to model that transition. And usually when you look at someone running, say, a full-on CFD, and they're doing a rotating rotor in time accurate analysis, they consider it a really big deal if they do 10 revolutions. So there is a fundamental, difference in time scales that you have to look at. And from the aircraft dynamics standpoint, the propellers really are a time averaged actuator disk kind of thing when you're looking at the rates of even short period and phugoid. And so you need tools that are mixed. And this is that's a question, clearly. The only other thing I'll add is that Dave Kinney's working on this. One of the things that's on his list, hopefully to do soon, is he's trying some even more simplified ways of modeling the rotating blades that will hopefully allow much faster modeling that would be appropriate, much closer to being appropriate for the aircraft dynamics type timescale.
Right, and we've been in contact with Dave about that specifically while we've been navigating, exploring the unsteady solver, and I think this particular case highlights the importance of a tool like that to kind of bridge the gap between something that is really fast and computationally efficient and something that could really blow up in timescale, like you mentioned.
Thanks a lot for that feedback. And we do have a couple other questions on the social Q&A, but it is 12:30. And in the interest of time, I think we're going to go ahead and transition over to Justin Gravitt to start the build session. But if we have some time to come back to these, we might follow up with Garrett and see if he can respond to some of this social Q&A. So thank you.
Certainly.
So, okay.
All right, so should be sharing my screen now. Let me know if you guys can see it.
We can. It looks good, Justin. Thank you.
Yeah, no problem. Would you like me to go ahead and just jump into it then?
Yep, let's just roll into it. It's 12:30 and we're right on schedule, so let's go ahead.
All right, great. So my name is Justin Gravitt. I'm with ESAero. And right now I'm going to be talking about how to set up your build environment, compile OpenVSP, and modify the source code however you wish, even giving back and providing improvements for the public version. This is specifically just for Windows. I kind of just went through with the software requirements that I recommend that I've recently built on Windows 10 successfully. There are other options out there. This isn't really going to cover building on Mac or Linux or anything like that, but it'll definitely give a good starting point for being able to compile everything and get yourself up and running on Windows. So I'll start by going through the recommended software that I suggest, then going through how to set up each of those different software packages, getting the source code, and then building two separate projects to get the full VSP build. So you first need to build the libraries, and then you could build VSP itself. Then I'll talk about how to run and debug the code in Visual Studio, and then finally how to contribute to OpenVSP through the public repository. So this is my list of the recommended software prerequisites. Like I said earlier, alternatives, they're probably going to work. These are just the ones that I've tested recently successfully. The only one that I would mention that I would specifically recommend against is trying to use 2019 Visual Studio. I have gotten it to work on one build system before, but I've also had it fail for me. We believe it's an issue with the 2019 compilers and one of the OpenVSP libraries, most likely libaegis. So I would recommend going with Visual Studio 2017. I believe the version that's bundled with AppVeyor is released on the OpenVSP website actually uses the 2015 compilers. So either of those will give you good results if you use them. But I use 2017 for this case. The next thing that you're going to need is cmake. And I just used the latest version for Windows 64-bit. And then you also need Git. Any Git GUI should work fine. I have the best experience with SourceTree. But you can use a different Git GUI if you prefer that as well. SourceTree also includes Git with it, so you don't have to download. If you're interested in the Python API, and this is especially important if you would like to use a different version of Python than what's bundled with OpenVSP, or excuse me, not bundled with OpenVSP, but used to wrap the API, such as Python 3.8, which I'm going to use in this example, then you'll want to go through the SWIG process of installing that and linking it with OpenVSP to compile the Python API yourself. So SWIG version 4.0.2 is the one I listed here. I might actually suggest 4.0.1 instead. This was something that we actually just found out this week. I was able to use 4.0.2 in this example, but actually using the latest version of SWIG, which is 4.0.2, to generate the latest version of OpenVSP on Windows that you can download on the website. There was some issue with the AppVeyor build finding SWIG. When we forced it to use 4.0.1, it found SWIG and compiled the Python API. That's been since updated, so if you now notice that you don't have a Python folder with your Windows download from the website, if you re-download it, both the 32-bit or the 62-bit versions, they will include the Python API as well. So that's just something to be aware of. We fixed it, so you can go ahead and update if you need to. For Python, I recommend Anaconda version 3. Just includes all the really nice packages that you'd want to use with Python, so you don't have to download them individually. And I'll go through the installation process of that because it can be a little bit strange when it's trying to add it to your path correctly and be able to be found by OpenVSP correctly. The last one that you could download, but most users really don't need it at all, is called Doxygen. If you want to generate the API documentation yourself, but available for download online, so probably not needed. So the first thing you're going to need to do to set up OpenVSP for building it yourself on Windows is create a GitHub account. Then you'll need to install Visual Studio. So for 2017, you'll have to make sure you check the desktop development with C++ workload package, and that'll include all the right compilers that you'll need with OpenVSP. That's the only one you need. You can always add more if you'd like, or you can also go back to the installer at any time and add more if you need them for other things that you're doing as well. You will need to restart your computer after you set up Visual Studio. The next, we'll install cmake. During the installation process, I'd recommend adding it to your system path as well. If you do that, you could test it by, after you install, opening up a Windows command terminal and just typing in cmake and see if it is found correctly. That just makes things easier. It's not a requirement. You could also add it to your path manually if you prefer, but that's just an option on there that I would suggest. The next thing I'd do is install source tree. In the installation process, I'd include Git, and that would just get you the latest version and everything. Like I said earlier, you can use a different Git GUI if you prefer, but this is just what I'm going to show here. And then the last one is Doxygen. As I mentioned before, it's an optional package to install. So when you download SWIG, if you're trying to build the Python API, I might have listed this earlier, but you'll want to make sure you download the Windows version of SWIG. I think it's called SwigWin or something like that. I could go back and check the link if I included it in there. But you'll extract the contents of it, place it in the directory if you like. If you're looking to build the MATLAB API, you'll actually need a different version of SWIG. You'll actually have to compile SWIG yourself. I'll be discussing that in the next presentation coming up. So in terms of the MATLAB API, this presentation and the next one are very much linked together, because if you're building the MATLAB API, you also have to compile OpenVSP from source yourself as well. When you're installing Anaconda, if you are using the Python API, I would highly recommend this check mark that adds Anaconda 3 to the system path variable during the installation process. It warns you against doing so. I've never had an issue with it, and we've had users at ESAero compile with Anaconda using this installation method without any issue. Otherwise, you'll have to add Anaconda to your path manually, and I've had issues with that with using the Python API. So this is just what I would suggest. Adding it to your path during the installation process just makes everything a lot easier. Once you install Anaconda, you can check that it's included in your system path correctly by just opening up a Windows command terminal, typing in Python, and making sure you can find it correctly. That's what I show on the bottom here. So it's finding Python version 3.8.3. So to get this source code, you're going to just log into GitHub, go to the public OpenVSP repository. From there, we would suggest forking a copy to your GitHub account. Then you'll need to clone that forked copy. So here I'm showing that done through the source tree GUI. So you just go to the new tab and then click on clone. You enter in the path to that Git repository. Then you could specify where you want those build files to go. What I would suggest is creating a folder somewhere, such as in Documents, and another folder called OpenVSP, where you can have separate folders for the OpenVSP repository, the source code, another folder for the VSP library output files, and then another one for the VSP build files. You could even have another one set up for the install folder, which is basically what you would see when you get OpenVSP from the openvsp.org. So that's what I would suggest, and that's what I'm going to show here. So clone the repository through source tree, or you can also do it through the command line if you prefer. You just need to make sure that you have Git in your path, or you open Git directly. Next thing that we're going to do once we have the repository cloned is we're going to add the public repository as a remote. So this allows us to get all the updates that are pushed up to the public OpenVSP, make changes on our own fork, and have those linked to communicate with each. So to do that, you'll go to, at least in source tree, repository settings, then you'll click the add button. And then you just need to set the URL path to the version of OpenVSP, which is github.com/openvsp/openvsp.git. So next, we'll need to set up the OpenVSP libraries. So there is a super project that you can build. That's actually one that I have not done myself. I've always done the approach where we build the library separately, followed by VSP itself. So this step, we're going to build the library. So you'll open up cmake. You're going to point the cmake to the source code, which is actually going to be a subdirectory within the source code that you downloaded or that you cloned previously. So there's a folder in there called libraries. That's what you're going to tell cmake for the source code. Where to build the binaries, I would suggest pointing it to a new folder adjacent to where you cloned the repository. So if you have a folder, which you could see here, called OpenVSP VSP repo, that's where I cloned from GitHub the OpenVSP source files. And then I have another folder adjacent to it called VSP libraries. That's where the library build files are going to be placed. You'll then need to add a cmake build type entry. So you do that in the cmake GUI by clicking add entry on the top right. You'll enter in with all capitals and underscores in between each word. You'll enter in cmake build type, and you have a couple of options there. The three ones that I'm familiar with are debug, release with debug info, and release. So debug is the best for debugging, but it's also going to make OpenVSP very slow to use. Release with debug info is a bit faster, but when you're debugging, it's not always right. Where associates its related debug object files with with the debug process. So you might be trying to walk through code and it might skip a line, then go back one. You might not be able to see using IntelliSense and Visual Studio all of the information that you need. So it's not perfect, but it also allows you to run OpenVSP very quickly. The release build allows you to run OpenVSP just as you would from downloading off the internet. It's the fastest way to run OpenVSP, but it also has no debug capabilities other than traditional adding print statements, things like that. I would recommend release with debug info, but if you're maybe a really new programmer, debug might be, and you are intending to make changes to the source code, debug would be the best choice. If you're not planning to make any modifications to the source code whatsoever, release is your best option. But if you're compiling OpenVSP yourself, you may be making some changes. So release with debug info is the best kind of happy medium between those two options. So next step in building the libraries, we're going to, after we opened up cmake, told it where the source files and the output binary or output files are going to be, and we added that cmake build type, we're going to click the configure. That'll pop up this window that you see on the left, or excuse me, right. We'll select from the drop-down Visual Studio 15 2017. You have Visual Studio 2017 downloaded with the 2017 compilers. If you're using 2015, make sure that you point the generator to Visual Studio 2015 instead. But this is all being shown with Visual Studio 2017, so we'll use that as the generator. The next drop-down, it defaults to Windows 32-bit. I would suggest changing it to 64-bit platform. Everything else you could just leave with the defaults, and you'll click Finish. After that, once cmake finishes, you could click Generate. You could ignore the one or two messages that pop up for warnings for project developers. And then once that finishes, you can open the VSP library solutions file that cmake generates. You could open that with Visual Studio. Once you open Visual Studio, you'll have to make sure on the very top you match your build settings with what you selected for cmake. So what I had done was I added a cmake build type as release with debug info, and I also used the 64-bit generator. So in Visual Studio, this is easy to miss because it doesn't always match automatically. Made sure that I selected release with debug info here and 64-bit. And all you need to do is go to build and click build solution. And so let's see if this will play. So this is just a quick video so you're familiar with what building the libraries is going to look like. It's sped up a little bit. Building the libraries doesn't take too long. Building VSP takes a little bit longer. So this is just so you're familiar with the sort of output messages that you should expect. Sped up just slightly. And so once it finishes, it'll say, build successful, or how many built successful out of how many that you tried to build. And those should match. This should finish in just a second. Jump ahead a little bit. All right, so there at the bottom we see 12 succeeded, 0 failed. So that's good. Once that finishes successfully, we're going to move on to building VSP. So just like before, we're going to open cmake. This time, instead of specifying the source directory as that libraries folder within the source that you downloaded, we're just going to use the folder of the clone repository. So the entire source directory. For the output files, similar as before, we're going to just use an adjacent folder. So instead of to that clone directory, so instead of VSP libraries, we're going to make one called VSP build or something like that. Similar as before, you add your cmake build type entry, debug release with deb info or released. you have to make sure that you match the cmake build type between the library's build and the build of VSP. So make sure those are the same. The next thing that we have to do is add the VSP library path entry. So that's what's shown on the right here. What that does is it tells cmake where the files that we just built through Visual Studio are for the library. So we add this VSP library path and we point it to where we just built the VSP library. So that's what's shown here, that VSP libraries directory. This has to be done after we compile the libraries through Visual Studio. This is an optional entry that we could add, the cmake install prefix. So this is if we're trying to build the OpenVSP distribution package. I have one that's just VSP install that's adjacent to the VSP libraries, VSP build, and VSP source directories. Swig executable, you can specify that if you are building the Python API. So you add the entry, specify the name as Swig executable, and you're going to point it to the executable for Swig. Similar as before, you're going to select configure, select the same generator and platform as before. So in this case, Visual Studio 2017 and the 64-bit version. Click configure and generate, ignore the warnings for project developers, and then go ahead and open the output files in Visual Studio, which you can do directly from cmake, or you can just find the VSP top solution file and open that. Just as before, set the build type and platform to match your cmake settings, and then click build and build solution. And so here, this is the output from cmake after I click the configure option. So originally we just have at the bottom here a cmake build type, cmake install prefix, VSP library path. So those are the ones that I added before clicking configure. Once you click configure, everything in red just is automatically populated. You'll notice that there's one that says FLTK dir not found. You can ignore that. Just make sure all these other ones are filled with a path as listed. On the right, this is an example of the output that is shown below. So on the left, I'm just showing the top part of the cmake GUI, and then on the right, I'm just showing the bottom part, which is the text output. And so here, something to look for is we found Swig and we found the Python lib. So this is important if you are trying to build the Python API. Here, this is just also showing a little video of the VSP build. I'm going to just skip through this, but I'll have it in these slides for later. This is just showing what to expect. It does take a little bit of time. This is sped up quite significantly, but this will be in the slides for if anyone would like to view it later. So now, these are some suggestions I have for setting up your build environment. So the first thing is, a lot of times this comes up when you just start running VSP for the first time. It won't be able to find VSP viewer, VSP arrow, and VSP slicer. So you'll need to add post-build events because those are separate executables. They need to be copied to the right place where OpenVSP will be able to find them through Visual Studio. So that's this information I have listed here. The next thing I'd suggest is to set VSP as your startup project. So you just right-click on VSP in Visual Studio, click Setup Startup Project. Otherwise, it'll default to, I believe, the All Build or something like that at the top, which is not something that you could just run or would want to run through Visual. Once you do all that, you should just be able to click the local window debugger. That'll allow you to run VSP. Next, this is going to talk through just how to contribute to OpenVSP, how to make modifications to the code. So in Visual Studio, I'd suggest changing your preferences to insert spaces instead of tabs. Just to be, when we're making changes to the code, we always just try to be consistent with everything else that's already in there. And that's, pretty much standard in OpenVSP. I'd suggest in source tree, if you're using that, change to a fixed column width for messages and add spell checking. Then you can create a branch off of the latest version of OpenVSP, which I'm showing here as OpenVSP 3.21.2. I right click and select branch, and then I create a new branch. Then you can make any modifications that you'd like to the source code in Visual Studio. You, of course, build those and test it. So here, I'm just showing an example of some changes I made to add a warning if you're trying to input a transonic Mach number in VSP Arrow. Just a really simple check and then a message output. So just a single commit in source tree, I review the changes. I add a commit message, which I recommend adding first a title, then skipping a line, and then adding a more descriptive message. Try to keep your commits really self-contained. Make sure that they don't depend on 2 commits later to actually compile OpenVSP. Try not to have one commit that has a ton of different ideas in it. Try to keep them a little bit isolated, understandable, easy to review if you are going to be trying to contribute to OpenVSP. Then you just stage the commits and push your branch to your remote repository. And the last thing that we're going to need to do is create a pull request. So you'll go to the public OpenVSP repository, select the pull request and new pull request options, and then you'll make sure you update the base repository in the head repository, which I'm showing here in this example. You'll then write a descriptive message, review everything, and then you'll create a pull request and wait for the administrators of the public OpenVSP to either reject, accept, or provide you some comments or even edits to your pull request. So hopefully that gives you guys enough to start with building OpenVSP yourself. Happy to answer any questions that you guys have.
Yeah, Justin, we've got a few minutes here, and we've had something come up on the social Q&A that says, if the end goal is an OpenMDAO algorithm with VSP in the loop, is it recommended to do the API build, or do you think scripting is enough?
So it depends what you're interfacing with, what tools. If you're trying to do things in MATLAB, you'll have to build OpenVSP yourself. If you're trying to use a specific version of Python, other than Python 3.6, which is used to route the latest version of OpenVSP, then you'll need to build OpenVSP yourself. But if you're just using, VSP scripts and things like that, then there's no need to compile OpenVSP. Hopefully that answers the question.
Justin, if you don't mind my jumping in.
Yeah, please do.
I think that's likely going to be dictated by the rest of your environment. If your MDAO process is already in Python, then use the Python connection that we already supplied. If your process is already in MATLAB, then you might want to compile the MATLAB API and use it directly from that, because that would probably be a good way to go. If you're writing a small, tight, but complex custom application, then accessing the API from C++ and writing your own C++ program may be the way to go. And then if you're doing anything else, sort of just ad hoc or scripting things together, then probably using VSP script is the way to go. So I think it's probably just they all offer the exact same functionality. It's probably just whatever is dictated by the rest of your tools.
Yep, completely agree. Thanks.
All right, well, we have a couple of minutes here, and I think we've answered any questions that have been posted to the YouTube live chat and the social Q&A. So we're just going to mute for about 1 minute or so, and Justin, if you don't mind, we'll go ahead and queue up the API and MATLAB discussion, and we'll go ahead and get started at 1 o'clock.
Sounds great. Thanks.
All right, so for everybody online, it's 1 o'clock, and we're going to go ahead and continue on our schedule with the OpenVSP API and the MATLAB or Python integration presentation. Again, this is Justin Gravitt from ESAero presenting. So Justin, it's all yours.
All right, great, thank you. So like Brandon mentioned, I'm going to be talking about all of the different API capabilities of OpenVSP. We have AngelScript, MATLAB, C++, Python. Some are a little bit easier to use than others, but I'll go through all the different types and try to explain them as best as I can. At any time, if the audio from my end is coming through a little bit glitchy or anything like that, please let us know and I'll try to repeat anything. But otherwise, just going to go ahead and jump right into this. So I'll talk through just an introduction about what the API is. I'll give an overview of the C++ API, the AngelScript API, the Python API, and then there'll be a lot of focus on the MATLAB API, which is the most extensive build process and integration process required. The reason I show Podman there is because custom geoms actually use the API, at least the AngelScript API. So what is the API? It's an application programming interface. We have a C++, AngelScript, Python, and MATLAB interface. It's used for automation. If you don't have GUI support on your operating system, you can use it to integrate with other codes without needing input and output files or anything like that. You can use it for testing, which is what we use it for a lot in OpenVSP, and also for custom geometries, like you can see with the seat component group custom geom. So there's also an image there of some plots that were created from running VSP through the API. So those are the sort of things that you could do with this capability. It's very powerful. It's mostly for people that are a little bit more advanced and used to OpenVSP, but there's a lot you can do even just as a new user. So opens the doors to a lot of possibilities, many that I couldn't even start to think of. So there's a lot you could do with it. It's some really neat stuff. So the old way to learn about the API was really just to study the source code. We didn't really have a whole lot out there other than workshop presentations and some wiki documentation. We provide examples as much as we can through the scripts directory that we get out with OpenVSP. But recently, there's actually been a Doxygen style documentation of all the functions and classes that are available through the OpenVSP API. So now that's kind of the place to start. So the API documentation, I provide the link there to just grab the latest version from the website, openvsp.org. You could download it directly, so that allows you to have access to it if you're not able to have an internet connection. And just some general things about the API functions. A little while back, the analysis and results manager were created. So previously, for every different analysis-based tool in OpenVSP, mass properties, CompG, VSP, things like that, there were functions specifically needed to run each one. What the analysis manager does is allow functions to be used to set up each of the analysis inputs to those tools, execute them, and then collect results through the results. The way we identify all the different analysis types are just through strings. So an example is like VSP compute geometry. To find out all the different ones available, you can use the list analysis function. And then to find out what inputs are available for a certain analysis, you can use the print analysis inputs API function. In the API documentation, and here as I'm explaining these, I'm just kind of writing out the functions generically. But however, the C++, Python, MATLAB API, they all translate pretty closely. So the API documentation kind of applies to all of them. Using the analysis manager is preferred as opposed to some of those old functions that I explained earlier that were initially available to run these different tools. And one thing to note is with the analysis and results manager, we use arrays for the inputs and outputs. So even if we just have a single input, it's still input into the analysis as an array. So just one thing to be aware of. So parms in OpenVSP. If you're not familiar with what a parm is in OpenVSP, pretty core concept to just data type of OpenVSP. So we have int parms, bool parms, things like that. Pretty much just a C++ data type with a lot of more advanced features associated with it, like limits to the parms, descriptions, an ID, so you can find that parm. And so in the API, we have just generic functions for controlling parm values. In the API, every parm, regardless of if it's an int or a bool, is going to be cast to a double. And each parm is identified, like I said, by an ID or a container, a group, and a name. So the trouble a lot of users have is how to actually find these parms and identify them. We do have examples that show how to control these different parm values, but there's a couple of ways that we can actually find them more easily. So the one option is just to open a VSP3 file, and I'll just real quickly show that. So if I just look at, let's see, a VSP3 file that I have, let's see here, something like this. You'll see it's an XML format, and we have all of these as parms. So we have the value of the parm, the ID of the parm, and so you can use those IDs through the API if you're reading in an existing VSP3 file. The whole concept with parms is that the IDs should never change. Another thing that you could do to find out the ID of a parm in GUI is, let me pull it up real quick. So if I just go to some sort of GUI slider input, and I click on it and click and drag it to any sort of text editor, that will show you what the parm ID is. So that's something that a lot of people aren't aware of, but it's a capability that's in there. You can also find out the parm name and description, things like that, by clicking on the parm button that's next to a lot of the sliders. This doesn't work for every GUI input, but in terms of like sliders and things like that, you could click on it. It'll pull up this parm info GUI that has the current value, its group, its description, things like that. So there's some ways that you can use the GUI to help you identify parms or the VSP3 file format. All right, so first one that I'm going to talk about of the supported languages of the OpenVSP API is the C++ API. So this is the basis for all the other ones because OpenVSP is primarily written in C++. We have functions that are in what's called VSP Geom API. It's in the Geom API project. That's where we expose a lot of the functionality of the GUI, everything under the hood, to a higher level that can be accessed through anywhere in OpenVSP, basically. Mostly the C++ API is used for our API testing. We have test suites for things like Parasite Drag, VSP Arrow. The idea is we try to run these every time we have a new version that's about to come out, just to make sure we're not introducing any new bugs and things like that. Those test suites are hopefully going to be expanded more in the future. There's a CFD mesh one that's being worked on right now. But the whole idea is to help us catch bugs and things like that. Also had them initially as part of our continuous integration builds, but they ended up being too time consuming. So there needs to be some work for those test suites at the moment, but we do have them in there. So the next thing I'm going to talk about is the AngelScript API. A very similar AngelScript is very similar to C++. You have to declare your variables. You have to have a main function in your script, things like that. But not quite as complex necessarily as C++ is. So AngelScript is the same language that's used for custom geoms and for advanced links. But if you're just running a regular old script, a VSP script, you'll use the VSP script file extension. And what we do is we take all of our C++ API functions that, as I explained, are written in that VSP geom API API file. We take all of those and we register them with AngelScript. But because of that process, we've sometimes missed functions in the past. So we've gotten a lot better at it. We tried to do an audit and make sure that everything in the C++ API is also in the AngelScript API. But that is something to be aware of and just part of the process that we have to deal with. We provide a lot of example scripts in the scripts directory. So if you download OpenVSP from the internet, from openvsp.org, and you go to the scripts directory that's included with it, you'll see a bunch of different examples that demonstrate API functionality. So this is a great place to start looking through those, running them. Just provides examples of API automation, things like that. There are two ways to run these VSP script files. The first is through the OpenVSP GUI, and that's what I'm showing in the top right there. You can click a file and then run script. And just point to any of those VSP script files that either in the scripts directory or ones that you've created. There's also a separate executable called VSP script that's included with OpenVSP that you can run through a command terminal. And there's an example there of showing how to run a VSP script. So the Python API and the MATLAB API too uses Swig, which is the simplified wrapper and interface generator. So what that does is it takes all of the C++ API functions and wraps them into a format for Python. The version of Python that you're using for running a Python script that is importing the OpenVSP API must match what was used with Swig to wrap the C++ API. So if you download the latest version of OpenVSP, which used Python 3.6 to wrap the C++ API, you cannot use something like Python 3.8 to run or import the OpenVSP Python API. Errors, the only way you can do that is if you compile OpenVSP yourself and use your own version of Python, like 3.8, to wrap the C++ API. So if you want to use a different version of Python with OpenVSP, you'll have to compile OpenVSP yourself. I mentioned this in the last presentation, but just to bring it up again real quick, if you did recently download version 3.21.2 from openvsp.org on Windows and you don't have the Python API included with it, go ahead and just download it again. That was missed, an issue with the app payer build, but it's included in there now. So somewhat recently, there were installation instructions included in the Python folder of OpenVSP, which allows you to install the Python API on your system. And there's also, excuse me, and I provide the link to that, those installation instructions there. There are two versions that you can use. There's a requirements.txt version and a requirements-dev text version. I've recommended the dev version. I've had better luck with that. And so that's what I would suggest if you are going to be installing the Python API. Once you go through that README following the instructions, you can open up a command terminal and type Python. Make sure that your system can find Python, so you have your path variables set up correctly. And then you could type import OpenVSP as VSP, and then try out either of these functions just to see if you could call the functionality of the the OpenVSP API. A couple of errors that sometimes pop up. The first is a DLL load error, which I show on the bottom here. And the problem there, if you see this error, it's probably because you're trying to use the wrong version of Python with the OpenVSP Python API. So if you notice here, I'm using Python 3.8.3, and I'm trying to use just OpenVSP 21.2 from openvsp.org. So that's the type of error that you might see if your Python versions are incompatible. Another thing that pops up is that the VSP error solver, the viewer, or the slicer are missing. If those pop up, you just need to copy those executables to wherever your Python executable is. They're not necessarily needed in every case, but if you are doing something like using VSP arrow, you will need at least the solver to be with your Python executable. Just real quick, Rob or Brandon, I'm getting a little bit of background noise. Is there a mic on?
Well,
Okay.
And I may be the noise. I'll go back on mute.
Okay, thanks. Let me know if there's anything that you might want me to repeat, or if users would like me to go back to. But otherwise, I'll just go ahead and continue. So next is the MATLAB API, and this is what pretty much the entire rest of the presentation is going to focus on. So it's pretty advanced and experimental. You have to compile multiple things yourself. So an unreleased version of SWIG. You also have to compile OpenVSP yourself. So it's really not recommended for new users. Requires you to have at least some existing software development skills. If you've never really compiled anything before, feel free to give it a try, but it might be a bit of a challenge. So what you've done, we've actually integrated the MATLAB API with our Panther toolset. This was done in a NASA SBIR Phase 1, the EIM disturbance rejection and conceptual design. So that was done by Nick Brake at ESAero. This is actually incorrect. The modifications made to OpenVSP, I'm not sure if all of them were released publicly. This is something that I need to work with Nick Brake with and update, but there may have been some things that were released publicly, but possibly not everything. So what we tried to do is keep the build process as simple as possible. We tried to also, duplicate the test suite that we have in OpenVSP so we can run it through the MATLAB API and make sure everything that we would expect to work, all the tests that we would expect to pass through the MATLAB API just as they would through the Python, C++, or anything. So in terms of setting up the Python API, what I would do is install Anaconda. I talked about this in the last presentation, but if you're trying to compile OpenVSP yourself, use a different version of Python, you'll need to install the latest version, add Anaconda to your system. But if you're just using the version downloaded from the website, you can just use this archive link to get Python version 3.6. You won't have to compile OpenVSP. You'll just be good to go with that version. So these are the two options with the Python API to get that set up. So I mentioned this earlier. We have two versions of SWIG. You could just use the latest one, 4.0.2, if you're going to be trying to wrap the Python API through a build that you're doing yourself of OpenVSP. There was a recent issue found with version 4.0.2. I was still able to use it to wrap the Python API successfully, but to avoid that, you could also just use version 4.0.1. But now for MATLAB, if you intend to try to get that API set up, you'll need this custom unreleased version of SWIG that supports the MATLAB bindings. So you'll need to compile OpenVSP yourself. You'll need Git, and I recommend source tree as the Git GUI to use with this. And then we've used MinGW with MSys and PCRE to get the Swig build to compile and run successfully. So the build process for the MATLAB version of Swig, this is just an overview here. I'll go through each step and explain those in more detail. But the first one is to clone the Swig MATLAB repo and check out the branch that we're going to use, the MATLAB custom doc branch. We'll compile Swig MATLAB from the source, which generates the Swig executable. What we then need to do is create a MATLAB API with the OpenVSP repository, which we use the Python API as a sort of a template for. We then point the cmake build to the Swig executable, so that allows it to wrap that API when you compile OpenVSP. We then compile OpenVSP, which I would suggest looking at the previous presentation if you need some information about how to do that. Delete a function in the Swig ref MATLAB file, and then just build the scripts and test everything out. Steps 2 and 3 are the two most challenging, and I'll explain why in a minute. So getting the Swig MATLAB repository, you're going to need to, which I've done in source tree, clone that repository. So at the bottom here, we have that the link to that repository. What we've done is we branched off of the MATLAB custom doc branch and just cherry picked 2 different commits, but that was what was shown last year at the workshop. Since then, I just used the latest Git SHA of that MATLAB custom doc branch. So you can just go ahead and use this one at the top here. So that's what that Git SHA is that I've listed at the bottom. You don't need these 2 cherry-picked commits or anything like that. So just go ahead and get the latest version of the branch. Once you've cloned the repository, you'll go into within that repository, the docs manual and Windows HTML file. In there, you'll find some instructions on how to build the Swig executable on Windows. So what we've done is we've done the MinGW with MSys approach. I'll explain that in a minute. There are other options. You could use Cygwin or potentially Visual Studio IDE, but we recommend the first option on there, and that's what's being shown in the instructions on the right here. So the first step that I took was to install MinGW through the installation package manager, and pretty much just installed everything except the ADA compiler. You don't need necessarily everything, but it doesn't take up too much space, and it's kind of better to have. So I just went ahead and installed the Fortran 1, C++, Objective-C as well. Primarily, you need the MinGW developer toolkit and the C and C++ compilers. So that's the top one here, this MinGW32 GCC, and this last one here, the MSys base, and also the MinGW32 base. So those are the 4 primary ones you need. You don't need the Fortran or the Objective-C, but you could go ahead and add them if you'd like. I did not modify the packages. I just used the basic setup. I didn't go in and select individual ones to install or anything like that. So I just used the packages that they have available here, the latest versions, installed those. Then what I did was I added MinGW and MSys to my environmental variables, so adding it to my system path. And so that's what's shown here. We have the MinGW binary directory and the MSys binary directory. I did not need to install Bison, AutoMake, or AutoComp separately. Those were already included in these packages that I installed through MinGW. I did have to get the this version of P. It's a library that you link. So there's instructions on there with Swig that's shown on the previous slide. So you can get it from either of these two links. You extract it in the Swig source directory, and then you run this this build script to basically link the static libraries correctly. So next, just following those instructions, you're going to need to run a configuration script, things like that. It's called the autogen. And so when I did that, I actually came up with a strange error message. It was basically shown here. It might not pop up for you. It might have just been the the versions of everything that I had on my system. The way I solved it was simply to delete the configure file that's output from when you run bash autoconfig or autogen, excuse me. So I deleted that configure file. I then reran bash autogen .sh. I opened the configure file that bash scripts generates, and I just deleted the lines that were failing. I know that sounds crazy, but it had to do with installing boost and checking for boost, things like that. I just deleted those lines, and that allowed me to build everything correctly. So in case that comes up, that's the way I approached it, and that generated the make file. I was then able to run make and generate the Swig. Step 3 in the build process is we're going to need to modify the cmake text that's in the source directory of the repository here, the OpenVSP repository. So we just copy add subdirectory and add MATLAB API. That's what this is showing here, the cmake text file. Then what we need to do is copy the MATLAB, or excuse me, the Python API folder, and rename it MATLAB API. And we need to make some modifications to those files. This is something that I actually had a little bit of difficulty with recently. Been working with Nick Brake to generate some, more clear instructions on how to do that. I will try to provide an update in a timely manner, but this is sort of just
we can probably make these changes in a branch and make that available, or even in a normal part of the repo.
Yeah, and that's actually something that I thought we had planned. It was discussed at the last workshop, and then might have just got left on the table. And I couldn't find the branch that had these changes on it, and I think Nick had a hard time finding that branch as well. So I do agree. It would be great to just add this to the public build and have it available for everyone, so no one has to go through this process themselves. They could just have it already available. So at the moment, we're going to be working on that. Hopefully provide an update soon and release it with the next version. And this just mentions the key changes to the VSP source, modification to control the VSP arrow path. That might not be necessary anymore. And then a reference to matrix.h had to be removed just to deconflict what MATLAB uses for its matrix class and what OpenVSP's C++ API uses for its matrix class. So once you set up the MATLAB API directory, which hopefully we'll have included in the next version of OpenVSP, and you have your Swig executable, which was compiled from the development MATLAB or Swig MATLAB version of Swig, then you just need to point cmake to that Swig executable using the Swig executable cmake entry. This is kind of going back to the presentation that I had earlier, which talks about how to compile OpenVSP. So you'll point cmake to that Swig executable, and then it'll use that to wrap the MATLAB API. You'll then compile OpenVSP, or excuse me, configure cmake. When you run that configure, button, you'll see these outputs. So it'll identify that Swig and MATLAB were found. It's going to compile these mix files for MATLAB. And of course, it'll identify the other MATLAB directories and library directories and things like that. So obviously, a prerequisite I should have listed is to have MATLAB installed on your machine. So then you could go ahead and go through the whole, the normal build process. And this was done through Windows PowerShell. Then in the swig-ref MATLAB file, there was a swig clear function that needed to be deleted. That's what's shown here. And then here is just showing the API tests. So we're going to want to run those to make sure that our MATLAB API build was all set correctly. And then that's it for the API walkthrough. I could do a couple of demonstrations. We still have plenty of time, but if there's any questions in the meantime, please let me know.
There have been some questions that have come up, but we've been able to answer, I think, them online, at least so far. So we can hang here a second to see if anybody asks any more questions for you to address verbally.
Okay.
But thanks for doing that so far.
Yeah, no problem. So one thing I'll show just in the meantime, everyone feel free to ask questions otherwise. I could just show how you could run scripts through OpenVSP just using the VSP script version of AngelScript, so you don't need to compile anything. You don't need to have any Python installed or anything like that. Let me see here. There we go. So for example, I could just copy this exact line. I could open up a command terminal into that directory, and then simply copy this. Oops. And that will go ahead and run the CP slice analysis. So what that is doing, which I could pull up that example as well, that's finding the CP slicer script here. And I'll change it so it's in C++ style. And so what that's doing is just adding a simple pod and a wing, setting some of the parm values, like the position between the wing and the pod, and then it's just setting up the file name. So that's what's going on here. Saving it to file, and then it's just setting up your VSP arrow analysis by computing the dgen geom file, or in this case, actually I might be using a panel method actually, and then just running VSP arrow and running the CP slicer analysis. So those are all the different things that are shown here. This is just an example. There's a lot more that are available that you could check out. Instead of running it through the command line like I did there, I could also just open up VSP, go over to File, Run Script, click on the scripts directory, and do the same thing. And if I look at the terminal, you'll see what's going on there, and you'll end up with your geometry. So you can use the API to generate geometries, or you can have an existing geometry and read that into the API. There's a lot of different things you could do. Pretty much anything you could think of that you could do in the GUI, you could do through the API, but without any user input. So you could just set up your script to run automatically, go through a sweep of different locations of things, running with VSP arrow, anything like that. You can do quite a bit. So we use it all the time at ES Arrow. It's been a very, very powerful thing to have access to. So we're definitely appreciative of it.
Yeah, and I'll add is from personal experience getting into scripting and the API itself, that if there happens to be something that you are trying to accomplish and you're not quite sure where to begin, You can always ask a question to the OpenVSP Google group, and either Rob or myself or Justin or somebody will chime in and usually point you in the right direction, because there might be a different way to accomplish what you're trying to accomplish. If it's something that you're trying to investigate on your own, you can definitely go into the OpenVSP API documentation. And from there, you can usually find the parameter or the command or the types of things that you're looking for, and that is going to give you a great place to start, because you can find how to, say, get the parameter ID for a particular component, or how to find a parameter, how to do a set parm val operation, all of this stuff. The syntax may be slightly different between the API or a VSP script, but a lot of it is almost identical. So it's a really great resource.
Yeah, and I'm just have that pulled up here now. If you guys haven't seen it before, each function is identified. We try to give a brief example of how to use it. Talk about the input parameters, the output parameters, things like that. So it could definitely be improved. If anyone has suggestions for improvements, please let us know. All right. Well, if there's anything anyone would like to see, still have plenty of time to do so. I'll work on making sure the Python API build we can support it through the release version of OpenVSP, just to make it easier for everyone. I know Nick Brake's done a lot of work on that. We just need to get it ready to get out there. So.
Awesome. And Justin, thank you very much for walking through the build and the API and all of this stuff together. I'll let Rob answer that OpenVSP4 question in the live chat. Because Justin is scheduled for yet another hour-long talk here at 2 o'clock, we're going to try and give him a nice break here for about 20 minutes or so to kind of rest and stretch his legs. We'll stick around and try and answer some of these questions in the chat, and then right at 2 o'clock, as a reminder to everyone, you can find the link to that session underneath your viewer. So if you click Show More, there's a link to session 3.2 right there. You can go straight to it. And right before 2 o'clock, we'll have session 3.2 live and ready to go. So,
great. Hey, Brandon, real quick, I'd actually like to show one more thing.
Yeah, absolutely.
That is API related. So, VSP part files that uses AngelScript as well. Uses custom geom API functions that are provided in the same API documentation as the rest of everything. We include with OpenVSP that you download from the website, this custom scripts folder has a few examples in there. A lot of people have made different ones, and you can open them, check out the source code of it. But what OpenVSP does is when you run it, it's going to look in that custom scripts directory, and if it finds anything and successfully reads them in, it'll have them available here. So you can look at something like the disk. You can see how it's parameterized, how it's set up in this VSP part example. Something else that I actually learned about recently is if someone provides you a VSP model and it has custom geoms in it that you don't have yourself, you can actually come in and go to, I believe, export, and click on this. Moved around a little bit recently, and click on custom script. So this is after you've loaded in the VSP file that you've received from someone else, and it'll actually list the custom scripts that it can pull from that model, so then you can have access to that custom geom yourself. So that's something pretty neat. We've created a few custom geoms ourselves, as Garrett mentioned in the previous presentation. We made like a ducted fan array, things like that. Pretty useful tool. So just wanted to throw that in there too.
And regarding that, if you have your own special sauce or your special components that only you are supposed to have, don't share your VSP model with those included. Break them apart or do something different with it. Because if you share that, then whoever you shared it with has access to that model.
Exactly. Yeah. If you actually look in the XML file, the VSP3 file, the custom geom code, like what's shown here, is actually in that file itself. It's embedded directly in it. So something to be aware of, like Brandon mentioned. All right. Thank you guys for listening, and I guess I'm going to take a quick little break here, but thank you.
Sounds good, Justin. Really appreciate the time. Go ahead and take a nice break, and by the time we get back, I'll have switched over to session 3.2, and we'll continue on there.
Great, thanks.